Okay, so today I'm going to be explaining addition reactions and the conditions which are required for these reactions to take place. So, at the base, addition reactions occur between alkenes and another reagent. And just a quick recap, should already know this, but alkenes are essentially hydrocarbons which contain double bonds. So, for example, we can have ethene, which is the most basic example, which looks like this. And they have a general formula of CnH2n. So ethene would be C2H4. And these alkenes can undergo reactions with reagents whereby the reagent adds to the alkene and essentially the alkene becomes an alkane with a single bond, and this forms simply by breaking the double bond present. So here we see an ethene that one of these bonds in here could break and bond with another reagent. So why does this happen? What makes this double bond, what does a double bond do which gives it the possibility to react with the reagent? So this is simply the fact that in a double bond, so let's just say this is the double bond, let me just draw it further apart. One of them is going to be a sigma bond, so let's say this is the sigma bond. And the other one is going to be the pi bond. And this pi bond has side-on overlap, side-on, which is relatively much easier to break than a sigma bond, because in the sigma it has end-on overlap, and it is the electron density is along the bond axis, which is much stronger than side-on overlap, which you'll see in pi orbitals. So they'll overlap sideways, which is much easier to break. So when these bonds break, but in the pi orbitals, these electrons in the pi orbitals are able to form another bond with another reagent. And generally, this is called electrophilic addition because of the free electrons which are made by the pi orbitals breaking. And this happens through the process of electrophilic attack by the reagent. Now, this all sounds very confusing, but I assure you it's quite simple and it's not too complicated. I'll show you an example later. The very simple example would be alkene reacting with a halogen, so we could have bromine or we could have chlorine. And so here I've got bromine, so we've got ethene plus bromine makes bromoethane, and really that's it. Essentially the bromine is added to the ethene and it essentially now has single bonds because the double bond is broken. That's just a very simple example. But there are a few reactions which you must know. So that would be ethene, when ethene reacts with steam, so that is just water at an extremely high temperature, which produces ethanol, which is an alcohol. And the conditions for this is at 350 degrees with a phosphoric acid catalyst. And these are just things you need to know, need to memorize. Really, to understand it is very, very complex. So just remember this. It's not too difficult to remember. The other reaction you need to know is when an alkene reacts with a hydrogen, which is called hydrogenation. And this occurs at 150 degrees with a nickel catalyst. So these are just reactions that you need to know, and yeah, there's really nothing much more to it. But if we go back to electrophilic addition, really this is just a simple reaction and it looks very like it only has one step, but that's not the case. There are the transition of electrons from one reagent to another is a lot more complex than just a simple reaction. So that's what we're going to be looking at, the mechanism of electrophilic addition. So we're going to be looking at the reaction between ethene, which we have here, and hydrogen bromide. So essentially, what happens, we need to understand the mechanisms by which the bond breaks between the carbon-carbon in ethene, and how the hydrogen and the bromine are added to the ethene. So the first step to this mechanism is the double bond breaking in the ethene, which we can see here. And this double bond, these electrons from the double bond will carry over onto the hydrogen. And these arrows that you see here are actually strategically placed, and they're highly intentional. So you can see that this arrow is placed like this, pointing towards the hydrogen. And you might be wondering, why is it going to the hydrogen and not the bromine? Well, that's also quite simple. Hydrogen bromide is a polar molecule because of the difference in electronegativities. This means that the hydrogen is partially positive, it has a partial positive charge, and the bromine a partial negative charge. And because this is a partial positive charge, positive attracts to negative. So we would call this hydrogen right here, we would call an electrophile, which is why this is called electrophilic addition. It is an electrophile because it loves electrons. It's attracted to electrons, which is why the electrons from the pi bond in the ethene molecule carry over onto the hydrogen, which really wants the electrons and forms a bond. At the same time, whilst this happens, bromine carries over the electrons from the hydrogen bromide bond, which makes bromine an ion. This breaking between the hydrogen and the bromine in hydrogen bromide is called heterolytic bond fission. So that all sounds very fancy, but it's also quite simple. So let's just look at it word for word. Hetero, we know from, for example, heterosexual, that is between two different genders. So that's different. So this means that the bond is breaking differently and unevenly. These electrons are going to the bromine, and the hydrogen is receiving electrons from the carbon. So that's hetero. Then bond is simply the bond, and fission is breaking. We know fusion is coming together, so fission is the opposite, it's breaking. Now, when that happens, the hydrogen bonds to the carbon in the ethene molecule. The double bond is broken, so it is not here anymore. It's just a single bond, a sigma bond. And the carbon here, because it has lost the double bond, which it had before, is now a cation. So we actually call this a carbocation. It's just a name for a carbon, which is a cation. And here we can see that the bromine is now an ion. And the bromine that is now an ion is negatively charged and has an attraction towards the carbocation, which has a positive charge. So the electrons from these lone pairs here will carry over onto the carbocation, and it will form a bond. It is very important that you draw this arrow very intentionally from the electrons to the position where the bond will be, so that it is clear that you know how the mechanism properly works. Then after this, we have the final molecule made. So we have bromoethane. And usually we just look at from here, these two reacting, and we go straight to here. But actually, we know the mechanism now, which is quite cool actually. So that's essentially the most important thing to know. Just a little side note is Markovnikov's rule. That's also a very big name again, but essentially all that means is that when a molecule reacts with a hydrocarbon, the hydrogen bonded, so for example here, will have attraction towards the carbon, so one of these carbons, which is bonded to the most other hydrogens. So that is only in cases where there's an uneven distribution of hydrogens bonded to the carbons. In this case, they are even. We have 2, so 1, 2, 1, 2. So it really doesn't matter too much. But in cases where you, for example, have 3 here, hydrogen, that's not actually possible, but let's say just we switch that out for a CH3, an ethyl group, a methyl group, then this hydrogen will definitely bond to this carbon because it has more hydrogens. That's Markovnikov's rule, essentially. It's quite simple. It's not too complicated. And that's basically it for today. Make sure to understand how to draw the arrows. It's called arrow pushing. Once you get the hang of it, it can actually be quite fun and it becomes quite clear what you have to do. And make sure to remember these conditions for these reactions. And yeah, that's basically it for today. Thanks for listening.